Hello, welcome. So this mechanism, it's unique because it tells you the product. So you need to get to this product. And if you look and you see over here, it turns from a pentane into a cyclohexane. So that means that there needs to be some carbon bonds that are going to be moving around, right? Now, the only thing that you've learned so far in this class on how carbon bonds can be moved around or even created, right, is just through what's called a methyl or a hydride shift. So you should come into this expecting that something weird's going to happen, and you're probably going to need some sort of shift going on, okay? Now, from your table, you should remember that this is a secondary alkyl halide, and it's being turned into an alcohol. And so the only thing that would cause this, right, would have to be some type of solvolysis, because you're adding an OH group, and because you're only adding an OH group, it has to be hydrolysis. So the reactant here is going to be H2O. Now, what that means, right, is a secondary alkyl halide reacting with H2O is going to be SN1. And that's just all based on the table, kind of looking at and mapping that out, okay? So we know it's going to be SN1, there's going to be carbocation, so let's start going through it. You have the pentane ring. And the first step, because this bromine, it doesn't have a hydrogen or anything, and the bromine's actually pretty stable in solution as just a negative charge, right? Because of London dispersion forces and because of how big bromine is, it actually stabilizes a negative charge pretty well. So we're comfortable being able to just pop this off directly without any pre-protonation or anything like an alcohol would require. So then we've got a secondary carbocation. Now, if you remember the reasons why carbocations are stable, the two reasons are for carbocation stability is induction and hyperconjugation. Now, induction is the idea that the more sigma bonds there are, the more electrons there can be that will gather around the positive charge and stabilize it. Hyperconjugation is that weird pseudo pi bond interaction, right, where you have the sp orbital between the hydrogen and the carbon. That's the carbon with the sp orbital. And then you have the other carbon over here with an empty p orbital, right? And what's going to happen is these electrons in this hybridized orbital will be jumping into the empty p orbital. Now, that would cause this positive charge to partially be over here, right? Now, for similar reasons of stability then, if there's more carbon CH bonds attached to this carbon, then that's going to make the positive charge in that actually prefer to be in that carbon's orbital because it's a more stable carbocation, because it's more substituted. Okay, so tertiary carbocation is more stable than a secondary, which is a lot more stable than a primary. And so because of that, these electrons will actually completely jump ship and might just take that entire CH bond and plop it over here. And that's called a hydride shift. Now, that could also happen with a methyl group. So, looking at this thing right here, this is a secondary carbocation. Is there another tertiary or quaternary somewhere else in the compound that might make it more stable? Well, you could potentially do a hydride shift from here, right? But if we look up at the product, that isn't what's happening. And so Blotto Sargent has said that if you see something that's unexpected, then you have to know, or you have to be able to, if you see something that's unexpected, it's okay to break the traditional rules. What that means is you've been taught to only do methyl hydride shifts from a secondary carbocation to a tertiary carbocation. But in this case, there might be a methyl shift going from a secondary carbocation to another secondary carbocation. And because he told you the product, then it's okay to go through that type of mechanism. So in order to get from this pentane ring to this hexane ring, what's going to happen is one of these two bonds is going to have to shift. Now, if we look at the molecule, either bond that moves will actually be okay, but for funsies, pretending that stereochemistry is a problem, right? We want the carbocation to be on this carbon. So if I call this carbon number 1, that means that this carbon here would be carbon number 1 because that's the one that's attached to the methyl group. And then this would be 2, 3, 4, 5, and 6. That would mean this is 1, 2,
You wouldn't number
3,
that
4,
way.
5, 6. Not for nomenclature, but for convenience.
Okay.
So now I can see that this 6 carbon is attached to the 1 carbon here. So that means that this 6 carbon needs to be attached to that 1 carbon somehow. Did I number those wrong?
Isn't there technically a number at the top of it too?
Anyways, doesn't really matter.
Because that's a
But-
carbon. What about this carbon on the very tip? Are
Yeah, you
just making
could
a
number that
methyl?
too, but I was just ignoring it.
Okay. So I guess it's gonna stick out.
Right. Anyways, sorry, the numbering's not super important. But what is important is that one of these bonds is going to shift. And for convenience, I'm going to pick this bond. So that means that this bond is going to shift and go to the carbocation right there, to the positive charge. And that's going to cause, this is where numbering is helpful. Where that's 1, 2, 3, 4, 5, 6. So I know 2 and 1, well, actually, so 2 and 1 will be connected, but what just happened is I moved the bond from 3 to 2 to 3 and 1. So my 3 is actually going to be to my 1, and attached to my 1 is a methyl group. Now, attached to my 1 is also carbon number 2, and we just removed one of carbon number 2's bonds, right? So that means that there has to be a carbocation now formed right there. And then 2 is connected to 6, and then 5, and this would have to be 4,
Beautifully done.
just like that. Okay? So now we have a carbocation right here, and what's going to happen is you have water in solution, and so water is going to go, and because it's a nucleophile, it's going to take care of that carbocation. And then, oh no, you have a positive charge in the solution. The way to get rid of the positive charge is by deprotonating it. And so another water molecule will come in and deprotonate that alcohol. Well, technically it's an alkonium or hydronium ion, but now it's an alcohol. And that looks just like our first product. And you could go through and play it around and actually try to shift this bond. And you'll actually find that it actually doesn't matter because either of those products would be the same because it's a racemic mixture. So, yeah, sorry this was a bit long. Hopefully the concepts make sense. Any other comments or questions?
No, that's great. Thank you, Annie. So is that right?